Welcome to this class. Now we'll be doing the proof that a set is a vector space in our today's section. Now looking at that, we need to first study the examples of vector space that we can have. Now a vector space can be represented by different equations and properties. Take for example, it could be represented as a set of numbers. It could be an integral, it could be a differential. Also, it could be in form of modular arithmetic. Now, when you talk about modular arithmetic, now you're talking about cyclic events like modulo, working in modulo 1, modulo 2, modulo 3. It also could be in logarithm, linear equations, quadratic equations, so many others that we are going to be looking at. So we have a variety of vector space, but the example we'll be looking at today will be based on the set of numbers, and we'll be looking at n-dimensional euclidean space. Now in n-dimensional euclidean space, we'll basically be looking at 3 or 2-dimensional euclidean space. Now in this first exercise we'll be looking at today, we'll be looking at a 2-dimensional euclidean space x, y. So we have this question right now before us. Suppose v is equals to x, y, such that x is in the 2-dimensional euclidean space and y also, and we have a scalar k and bk in the field, and we have a vector addition and scalar multiplication that we are going to follow to show whether V is a vector space or not. So let's quickly look at how we are going to prove this vector is a vector space or it isn't. Now we need to look at all the 10 properties, and then we can take a look at any of these 10 properties. When you look at commutative law with this vector addition, you will see that if you interchange x, y1 with x2, y2, it is also going to be commutative. You will be having something like x2 plus x1 on the right side, y2 plus y1, which is also the same thing as x1 plus x2 and y1 plus y2. So we can say that it is commutative. But this does not mean it is a vector space. It has to obey the other 9 properties, the other 9 conditions. And we are also given our scalar here. We have k in bracket s, y is equals to k s, y. Now the scalar tells us that whatsoever we are multiplying the vector addition in a vector, it must only be multiplying the linear dimension. Now remember that this is a 2-dimensional euclidean space, so it's only going to be multiplying one, not the other. That's why we have kx, y. Now for every u that is in big V and a, b that is in k, we have our distributive property of scalar, where we have a plus b open bracket u is equals to au plus bu. So now u is x1, y1. So we have to prove from our left hand side. So when we prove from our left hand side, we have this. Remember, according to the scalar rule says k bracket s, y is equals to what? Is equals to kx, y. So that means when we open that bracket, a plus b is representing k. It only multiplies x, obeying the scalar rule given in the question. So we have on our left hand side a plus b in bracket x1, y1 as our equation 1. Now let's go to the right side to see if we have exactly the same thing. Now going to our right side, we have au plus bu and we know what u is x1 comma y1. So we have a open bracket x1 comma y1 close bracket. Also, we still have to follow the scalar rule. Following the scalar rule, we only multiply the scalar with one of the x component, the x components of the what of the vectors that we are given, because that is the rule. So that means we have ax1 comma y1 plus bx1 comma y1. So we have followed the scalar rule given to us in the question. So when we add both sides, we will be having ax plus ax1 plus bx1 comma y1 comma y1. So we then realize that we have a plus b in bracket x1 comma 2y1, which is our equation 2. Now, of course, something is strange. Equation 1 and equation 2 could have been the same here, but the only difference here is that in equation 1 we have comma y1, in equation 2 we have 2 comma y1. So when we compare these equations together, you will see that it is not distributive and it is not a vector space, since it doesn't obey the distributive law. So it takes only one property not obeyed for a given V not to be a vector space, while it could still obey the other 9. But as long as there is one that is opposing, as long as it doesn't obey one law, it means that it is not a vector space. For it to be a vector space, it has to obey the 10 properties, the 10 conditions given in our first episode. And then different questions are to be attempted differently, because different questions will be solved differently. Now here we are making use of distributive law. In another question we could look at it could not be commutative. Now let's take a look at that. Let's look at exercise 2 and see other examples at it where we have to make use of other conditions. So in exercise 2 we have shown that V, which is also a two-dimensional euclidean space, we have x comma y such that x is in R squared and y is in R2, that is two-dimensional euclidean space. Close the set. It's a vector space or not with respect to the below operations. So we have x1 comma x2 in brackets plus y1 comma y2 also in bracket. This gives us x1 comma x2. Now this is a given rule for our vector addition. Now let's look at our scalar rule. Now this is kx1 comma x2 is equals to kx1 comma kx2. So we test for commutativity. So testing for commutativity in this question, we know that in commutative law we have u plus v is equals to v plus u. That is our rule for commutativity. So when we apply that to the rules given to us, we take a look at the vector addition rule, since commutativity is under vector addition, one of the conditions under vector addition. So we take that. We take our first operation, which is x1 plus x2, x1 comma x2, sorry, bracket plus y1 comma y2 is equals to x1 comma x2. Consider that as our equation 1. Now to test for commutativity, v becomes u, v comes first, u comes second. So x1 comma x2 is our u, y1 comma y2 is our v. So what do? We simply have a result to be y1 comma y2. Why? Because in the rule, the first vector is repeated in the right hand side when adding addition with another vector. So you will notice that this operation is not commutative, because when y1, y2 is added with s1, it yields back the first vector given, which is y1, y2, but it's not so for equation 1. So you can see that this operation is not commutative. That is, v plus v is not equal to v plus u in the operation given to us. So since it's not commutative, you can see that it is not a vector space. It is not a vector space. Now we can apply this knowledge to all other questions in vector space. You could also drop your questions, difficult questions under the vector space in the comment section. Now, in general, to attempt any other question in vector space, you have to consider the two operations given in the question. The two operations given in the questions will entail whatsoever, regardless whatever you are going to do when you prove with any of the 10 conditions given. In example now, just like the last example we did, we saw that it is not commutative. This does not mean it won't obey every other rule. Now take for an example, for the vector addition to old, for x1, x2 in brackets plus y1, y2, which is equal to x1, x2, it means that we'll be making use of the additive property, where y1, y2 is a zero vector, at least it has coordinates 0, 0. So when you look at that vector addition to old for the additive property, where x1, x2 plus 0, 0 will yield you back the first vector, because x1 plus 0, x2 plus 0 is still the same thing as x1, x2. So that vector addition operation given the question holds to additive property, but it doesn't hold for commutative property. And then for V to be a vector space, it has to hold for all 10 conditions. So in our next class, we'll look at more examples. Then we'll move to subspace.